In today's lecture, we will be covering transition metal chemistry, periodic trends. Jumping right in, when looking at effective nuclear charge, if you remember from main group chemistry, the p orbitals were poor at shielding nuclear charge. Do you remember why that was? It was because the p orbitals have a strong directional component. That is, they only point in certain directions, and they are orthogonal to each other. Therefore, they do not come in between the nucleus and each other, so they do not effectively shield nuclear charge. Even though electrons in the same orbital can partially shield each other, it is not enough to counterbalance the buildup of positive charge in the nucleus as you go from left to right in a period. What does shielding have to do with transition metals? Asking the same question in another way, do d orbitals and p orbitals have any similarities? In some ways, d and p orbitals are very similar in that d orbitals are also bad at shielding because they only point in certain directions, and they don't get in between each other and the nucleus.
D orbitals are a bit better at shielding each other than p orbitals,
but they still aren't very good at it. A consequence of this is that as protons are added to the nucleus and electrons are added to the d orbitals, effective nuclear charge increases. Even when electrons are paired in an orbital and have pairing energy, this is not enough to counterbalance the addition of protons to the nucleus. F orbitals are also bad at shielding for similar reasons that d and p orbitals are bad at shielding.
they are slightly better at shielding each other than d orbitals, though,
because there's slightly more overlap. So how does the poor shielding of d orbitals influence the atomic properties of the transition metals? Well, unlike the main group, the periodic trends in transition metals are far less regular. Across a row, the atomic radius stays roughly the same or decreases slightly. Can you explain why this trend arises? It's because the d orbitals only point in certain directions, and they do not come in between the nucleus and each other, so they do not effectively shield nuclear charge. Even though electrons in the same orbital can partially shield each other, it is not enough to counterbalance the buildup of positive charge in the nucleus as you go from left to right in a row. Therefore, the d electrons experience a greater effective nuclear charge as you go further right in the row. The radius does not decrease as much as in the main group, however, because the d orbitals shield each other a bit better than the p orbitals do. Another consequence of the poor shielding of the d orbitals is the d block contraction seen in group 13, which is right after the transition metals. The atomic radius does not increase as much as expected down the group, and aluminum, gallium, and indium have very similar atomic radii. This is because 10 protons are added to the nucleus across the transition metals, but the nuclear charge is poorly shielded by the d electrons. Therefore, the electron that gets placed in the p orbital in group 13 experiences a very large effective nuclear charge. Switching back to the d block, you can also see that down a group the atomic radius stays roughly the same or increases slightly in some cases. Can you explain why atomic radius doesn't increase as expected down a group in the transition metals? This is because of the F block contraction. The F block goes right after group 3, where the trend of increasing atomic radius down a group starts to fall apart. And you can see that the transition metals directly after the F block are not as large as you would expect. This is because the F orbitals are bad at shielding nuclear charge just like the d orbitals, and for the same reasons.
they're a bit better at shielding each other than the d orbitals,
But there are 14 groups in the F block. So you essentially add 14 protons to the nucleus across the F block, but don't shield the charge effectively with F orbitals. Therefore, when the d orbitals start getting filled, they experience a greater effective nuclear charge than expected, and atomic radius does not increase much at all. Looking at the electronegativity of the transition metals, across a row, there is no real trend. I have yet to hear a clear explanation as to why this trend is so irregular. Down a group, electronegativity increases, although the trend isn't the most consistent. How does this compare to the main group trends? Down a group, the trend for the transition metals is the opposite of the main group trend, where going down a group, electronegativity decreases. This could partially be a consequence of the poor shielding provided by the f orbitals, but electronegativity kind of falls apart for the transition metals. For example, in rhodium-hydrogen bonds, the electrons are polarized towards the hydride, despite the difference in electronegativity between hydrogen and rhodium. A major reason why electronegativity falls apart for the transition metals is likely the origins of the Pauling scale, which was developed for the main group elements. Also keep in mind that the Pauling scale is qualitative in nature. Looking at this graph of ionization energies again, but now focusing on the transition metals, is there a clear trend? Kind of, but there is a lot of variation. Across a row, as shown right here, ionization energies generally increase with increasing effective nuclear charge due to the poor shielding of the d orbitals. And down a group, so kind of there, ionization energy generally decreases except after the F block due to the F block contraction. And you can see that right here. This is where the F block contraction really hits. So this would be the F block, and then here are the transition metals after. Higher ionization energies for the third row transition metals are also due to relativistic effects. So I've mentioned relativistic effects for the transition metals several times already. And this is essentially the same thing as the inert pair effect that we saw during main group chemistry. Relativistic effects are seen mainly for the third row transition metals, which are in the sixth period. This is something you will hear a great deal from transition metal chemists, first, second, and third row transition metals, which actually refers to elements in the fourth, fifth, and sixth periods. In this course, I will likely interchangeably use the different designations. Anyways, relativistic effects help explain some unusual reactivity and properties seen for the heaviest transition metals. The most striking examples start at group 10, or with platinum. Where do relativistic effects come from? Well, they come from the radial distribution of the 6s electrons. And you can see you have your five radial nodes, and the penetration of the 6s electrons close to the nucleus is what causes these phenomena. The nucleus is so positive and charge dense that the electrons in the 6s orbital approach the speed of light to prevent from collapsing into the nucleus. At these speeds, the electrons behave like massive particles with large amounts of inertia. This is pretty much the same explanation as was given for the inert pair effect. We've already seen how relativistic effects influence the bonding in elemental mercury. And we briefly touched on how they cause an increase in ionization energy for the third row transition metals. The reason this is so pronounced is because the s electrons are the ones that are preferentially ionized first for transition metals, and because of relativistic effects, they require more energy to ionize. Lastly, the yellow color of gold can be attributed to relativistic effects. If you remember from last lecture, we discussed that metals are shiny due to the fast absorption and re-emission of light on their surfaces. This happens because the valence and conduction bands have no band gap. Moreover, if all light is equally absorbed, then the metal appears silver in color. Gold, on the other hand, absorbs blue light more efficiently and appears yellow. This increased absorption is attributed to the bands arising from the 6s and 5d orbitals. Normally, the energy difference between these states corresponds to UV light because the 6s orbital is higher in energy. Due to relativistic effects, however, the energy of the 6s orbital is lower than expected, and the energy difference corresponds to blue light. As such, gold absorbs blue light more efficiently and appears yellow. When looking at the general reactivity of the transition metals, they can be separated into two main groups: early and late transition metals. The early transition metals include groups 3 to 7. The early transition metals tend to be relatively more electropositive because the valence electrons experience a lower effective nuclear charge. They also tend to adopt high oxidation states up to +7 in order to adopt a stable electronic configuration. In lower oxidation states, where they still have d electrons, early transition metals are very good pi bases and are fairly soft. We will look into what a pi base is later on, but in short, filled d orbitals can act like lone pairs and donate electron density to pi acidic ligands. Within the early transition metals, there is a distinction between groups 3 and 4 as well as groups 5 to 7. Groups 3 and 4 generally lose all their valence electrons and form hard, highly charged ions. Therefore, they bond more readily with hard donors, they don't bind pi acidic ligands tightly, and their metal carbon bonds are very reactive. For groups 5 to 7, when the metals are not in their highest oxidation states, they are softer, they bind pi acidic ligands very strongly, and form strong metal carbon bonds. Late transition metals, on the other hand, include groups 8 to 11 or 12, depending who you are talking to. We will address this very shortly near the end of this slide. Late transition metals tend to be more electronegative due to the larger effective nuclear charge experienced by their valence electrons. They generally adopt lower oxidation states, which means they often have multiple d electrons. Some examples include iron 2, copper 1, etc. They are weaker pi bases than early transition metals in low oxidation states because of their increased electronegativity and harder nature. Late transition metals tend to form stronger metal hydride bonds than metal carbon bonds because of their harder nature. In addition, the first row transition metals are the hardest because of their smaller sizes, so they generally bind harder Lewis bases. As you go down the groups, though, the metals get softer and show a preference for softer donors. Please keep in mind, though, that hardness and softness are all relative and depend on the oxidation state of the metal, what the charge of the compound is, what species are bonded to the metal, etc. With respect to group 12, sometimes these elements are not classified as transition metals because they have completely filled d orbitals, so they have somewhat different reactivity. They have lower electronegativities, higher ionization potentials than would be expected for most of the rest of the transition metals. Moreover, they almost always adopt the +2 oxidation state, except for mercury. They behave a lot more like late transition metals, though, in their reactivity, as opposed to early transition metals. I personally think that this distinction is really silly because group 12 metals form metal complexes just like the rest of the transition metals. They have d electrons, they lose the s electrons preferentially, etc. Furthermore, understanding the chemistry of group 12 elements uses the exact same concepts as groups 3 to 11. So I personally usually just lump them in with the transition metals, but it's important to know that there are people who do not classify them as transition metals.
This concludes today's lecture. If anything was unclear, please feel free to ask questions during office hours or try rereading the textbook to clarify concepts. And as always, there are some useful websites and resources in the links below to help with understanding some of the concepts that were presented today.